Hey guys, welcome to AlgoYogi, and if you're not already signed in on algoyogi.io, please sign in to track your LeetCode problems that you have solved or you're about to solve or you're working on them, and then you can come and mark solved here. This is a great way to track your problems. Okay, let's go to our first problem that we are solving today. That is binary tree in order traversal. Now, I have already created on this long video on tree theory and tree traversals, so you can check that out. The link will be in the description. But we will do this problem in detail here as well, so you can stick around. So let's switch our view to understand the problem and what it is really asking us to do. And what is in order traversal? So let me switch my view here. So I have created this example here where we have this small binary tree, and I have labeled things here. This is our root, left child and right child. And the way we process our, so traversal means we want to visit all the nodes in our binary tree. And in order traversal, the way we visit our nodes is first we process the left child or left node, or you can say left subtree, and then we process our root, and then we process our right subtree or right child. Now, if you see over here, if you see in this small example, we have our root, and then when the problem is being asked, we will be given access to our root. Using the root and the left and right child pointer, we can visit these nodes. Now, first, if we think about it as a recursive solution, because tree is a recursive data structure, meaning this is a tree itself, but if you go to the left child, this in itself is also a tree. Even an empty node is a proper tree itself. Now, if I want to solve this problem using recursion, I will have a base condition where I'll be checking if my root is none. If it is none, then I return. Otherwise, what I want to do, I want to process my left child. And why in our recursive solution, I don't care how my recursive solution will bring out the problem. If I can solve, I don't care about how my big problem will be solved. If I can keep calling on my sub problems and I have a correct base condition, and I'm processing, when I reach my base condition and I'm processing that data right, then it should bring me the overall solution back to me. It should give me the final solution of the entire problem. So now I have access to root. I call the same function on my right, that do the level order, the in order traversal here on 2. Now this we'll call it on left. It's not present. Now it will process itself because that's how it's done in order traversal. We're going to process the root, so we will print 2. Then it wants to process right child, but it doesn't have any, so it will go back to the root. That's how things are done, right? It goes back to the problem where it was called before. So it goes to root, which is 1, it prints 1, and then it goes to the right child, which is 3, and because it doesn't have any children, then it's gonna print this as well. Now you can see, if we run this approach on our first problem, then it should give us the same answer. So here, if I call our recursive solution on 1, then it's going to call on its left child. It's not present, it's going to process my root, then it's going to call on child, but this is not a node which doesn't have right, left and right, so it has to process itself first. So in order to process itself, it will call on left and then right, left, then itself, and then right. So it will call on left, it will print 3, right, process itself, 2, right is not present. So that should be our answer, which is the answer here. Now Okay, we know this recursive solution here. Now I want to cover the iterative solution also. In iterative solution, so let's try implementing the iterative solution now. And the way we will be doing it is using a stack. Now we already know what this is. This is the order we visit our nodes. And the way we will be solving is using a stack. And even in recursion, the way things are happening are also using stack, but that is done by the machine, you know. Here we will be doing it ourselves. The reason we want to use stack is so that we can store these nodes and come back later to process them, right? So we go to a root, which is our current node, and we don't, because it's the root, we don't want to process it yet, but we want to keep going to our leftmost child, and on the way we just want to store all the nodes that we have so far visited. So we have visited 1 because we are right here, then we go to 2, and then we go to its left, which is none. Then what we do, we pop from the stack, and we process it. So I'm gonna pop it from stack, so which is, I'll just take it off. We process it, we print it, and then we go to its right. There is nothing, so we go back to the root. But going back to the root means I have nothing to do here. Then it means just popping my root. Pop root, process it, and then go to its right. I go to its right. This is out, by the way. This is out. Go to its right, and then put it onto stack, and then go to its left, which is not there. Then I come back up, I pop my value from the stack, then I'm gonna process it. Okay, so processing it, and then process the right, which is not there. Then my stack is empty right now, and my current pointer is none, which is over here, and there's nothing in my stack to go back to. So then this is the answer right here. Okay, so let's implement our solution without just wasting too much time. Now let me switch the view here. Okay, so I think here things will become more clear as we implement our solution. So what our question wants us to return is the array of values in order traversal, right? If you follow in order traversal on the binary tree, and the way you visit the nodes, just give us an array of those values. So okay, let's just do it. Let's call it answer, and we're going to have it as an empty array. Then we're gonna first we are implementing the recursive solution. So I'm gonna implement this inner function. I'll call it in order rather than calling the in order traversal, and it will take root, and it will check the base condition. If my root is none, then it's gonna return. Otherwise it will call this function on my left child. Okay, so it's calling on left child, but then there will be a time when the left will be none, and it will return back to where I made the call to this function, which is left, and that's the point where I want to store the value into my answer. That's where I want to process that. That will be the leftmost child, which has a value. It's not none or null. So I want to append my root dot value there. Okay, and then I want to process my right side. In this way, and if I call this function in order on my root and return my answer, then it should be all fine. It should run all fine. Okay, so the solution is accepted. Now the time complexity for this solution is big of n, because we are visiting all the n nodes. If there are n nodes, n is the number of nodes. So I'll write it. I think it's a good practice. You always, once you're done writing the solution, you are writing down the time complexity. Complexity. Oh my god, complexity. Is that the right spelling? Yes, okay. I don't know. Anyway, big of n, where n is the number of nodes, and space complexity is also big of n, or you can call it 2n, because we are storing the values and also putting things on stack, right? So space complexity is also big of n. So this is a recursive solution. We are done with it. Now let's do the iterative solution also, and we will be using a stack over there. So honestly, that is also simple. We'll maintain a stack, empty stack, and then we will have our current node, which will take our root, and then we want to keep going. We want to keep processing while we have stack and or we have our current node. Why? Because if I have something in my stack, then that means I haven't visited all my nodes, and current pointer, the things that we will be doing inside is going to the leftmost, process it when you have nothing to visit in the left, and then process your right. But the way you process it, you push it onto your stack. Okay, so you have to process your current node as well, and then also your right. So the way we will be doing things here is we wanna keep checking if my current node, then I want to push things to my stack. So stack.append my current node. Okay, now I have appended that. So if, let's say, if I were on my root, I have appended that to my stack, push to my stack. Now I'm using a normal array here. I mean, in other languages you'll be using push and pop. Here this is fine, like appending is fine, because we're doing the same thing with push and append. Now what you want to do from here is you want to keep going left. So my current node, which I've already pushed, now will go to my current node dot left, and it will keep going left until my current node becomes none. Go to the leftmost, go to its none, then it returns, because this while condition will become false. Now you come out, then this is where you want to assign what was last pushed from the stack. What was last pushed from the stack? The node, the leftmost node, where I called, basically assigned this value, current node. So I don't want it to none anymore. So what I'll do, current node equals to my stack dot pop is basically popping from the end of my stack. Now when I have received this value, I want to add it to my answer because it is the leftmost non-empty node. Okay, so answer dot append what my current node dot value. But at this point, I'm not done processing this subtree, right? Or even if it is, if it was the leftmost tree, I have to process its right as well. Doesn't matter if it doesn't have right, then it's our root we are processing. So we are done processing left, or left also is a root itself, right? So in that way we can think about it, that now we are done processing root, we have to process right. So in order to process right, I have just simply I'll just simply assign my current node to current node dot right. You see, now this is correct, right? Yes. Now that current node which was popped from my stack, which was storing the information basically, I pop it out. Now from here it will go back over here. Sorry about this typo. It will check stack. It might have it, it might not have it. Let's say it doesn't have it. Then let's say it was at the root level and root was the element that you popped out, then it wouldn't have anything. But your current node is still there, so which has to process its right, which will come down here and it will process them. Okay, it will process them from here. It will first process here and then process its left and that particular node, and then it's left, and then it's right, because it became a subtree right at that point. So now at this point we will just return our answer, and if we have what we have imagined and what we have typed is correct, then it should give us correct solution. Nope. Okay, because it's a typo, because here you see the way node is defined is it's val, not value. Whatever. Oh, you know what? We didn't submit the solution last time, but even let's submit it right now. Let's submit this solution. And let's also submit our this solution. I think they're both correct, so we're all good to go. 100%. Okay, we're done with in-order traversal. Let's go back to our AlgoYogi and mark it done. Sorry, it's just refreshing right now. If I refresh it, then it should have these problems over here. It will be marked solved. Okay, please check AlgoYogi out. Use it. I'm sure you'll enjoy going to LeetCode from here and marking these problems solved, and it will track your progress on the overall progress bar and the topic that you're currently working on, and then all the important problems that I've selected from LeetCode, so that once you're done with these, you're done with the trees. You'll feel really confident on trees part, at least, if you're done here. Anyway, thank you guys. Please like, share, subscribe. Okay, bye bye.